So, good evening, everyone, and welcome to the third LatentView RBCDSAI Colloquium. And this Colloquium series is enabled through the generous funding from one of our alumnus, Mr. Gopi Koteshwaran. And I have the great pleasure today in welcoming a distinguished alumnus of IIT Madras to be the speaker at the Colloquium, Dr. Ramanathan Guha. And in fact, I don't know if Guha remembers, the last time he actually visited IIT Madras and gave a talk, I was his host as well. That was when he came to give his distinguished alumnus acceptance speech. And so Guha is legendary, and in the especially in the open standards community, and he is the person behind the standards such as the RDF and also the RSSB. And his current passion is right now with DataCommons. He's the creator of DataCommons and also is leading the current project. He's a Google Fellow, and it gives me great pleasure in hosting Dr. Guha at IIT Madras once again. So Guha, over to you.
Thank you so much, Professor Ravindran. It's always good to be doing things with IIT, and I hope the next time we do this, it will be in person. So let me get started and talk to you about the thing that I'm currently working on, which is called DataCommons. And I should also mention that this is not just a Google project, it's a collaboration with many universities, most notably IIT Madras. And we are with Professor Ravindran and one of his students, Imran, and others who are on the call. So what is the context of this is, stepping back, we're all, AI is a big focus nowadays. I've been in sort of doing AI since about 1987. And if you take a step back from the particular mechanisms that we use to build it, to exhibit intelligent behavior in a domain, a system needs to have some knowledge about that domain. This is the so-called knowledge hypothesis that Raj Reddy and Ed Feigenbaum and Alan Newell and so on put forward. And it has to be able to use that knowledge. In today's terminology, we would call this, it needs to have a model of the domain. Now, model building is not a new thing. As in, like, it was not invented or introduced by AI or computer science. Serious model building started in hardcore civil engineering. Much of the advance in engineering that we see all around us over the last 200, 300 years comes from our ability to build better and better models. Now, it's not that we always had models. St. Peter's Basilica does not have a model. The temples in Tanjavur don't have a model. Kitty Hawk Plain did not have a model, but when you get into much more complicated structures like the Airbus 380 or the Burj Khalifa, you absolutely need to build explicit models. Now, the kind of models that we have been building in engineering for the last several hundred years are what I call analytic models. They are basic equations of the physical world. Continuum mechanics, material science, heat transfer, all of these things, which are typically fairly concise formulae, which capture the causal relationships underlying the phenomenon that is taking place. And in fact, if you look at a course in engineering, a program in engineering, there's a couple of courses devoted to each of these family of equations. There's a couple of courses in thermodynamics and a couple of courses in strength of materials and so on. And you could look at these as each of these courses is looking at a particular class of models around a particular class of variables. And yes, computing did come, and when we had to build incredibly complicated artifacts, like if you wanted to estimate that the wings of the Boeing 787 can twist by 26 feet, but not 28 feet, you needed to go into computing models. But still, these models were also built along the same lines, which is that you had a small number of equations that captured the underlying phenomenon, and then you modeled it, and you use computers to essentially scale the calculation part of it. In AI itself, analytic models were the first ones to be explored. Symbolic AI can be seen as this giant exercise in classical model building. There wasn't that much focus on having a small number of equations. So if you look at the expert systems ranging from the first ones, Mycin, to the most recent ones, like the FAA system in the US, the Federal Aviation Administration systems which guided planes, until about a decade ago, it was a giant expert system. And it had a ton of different rules. And eventually, this is what I call the boring stuff, but it's the important stuff. It just got absorbed into mainstream computer science. And now, if you open up any package from any of the big enterprise resource planning vendors from SAP or Oracle, you'll find some rule system underneath. You no longer think of it as AI. The really hard stuff in AI, which is common sense reasoning, became the focus. And again, there were several explorations of the kind of knowledge that you assume a 5-year-old has, but our computers still don't have. And there was an attempt with projects like Psych that I was part of, and many other projects in trying to figure out if we could somehow build this level of intelligence with just using this approach. The problem is that we don't have the basic equations for these kinds of phenomena. And then scaling beyond, there are really complicated, interesting social, medical, behavioral, economic phenomena. How do you predict, what is going to happen when you have a train full of people like that and there is, potentially some, Delta, Gamma variant going around, or what the market is going to do, or the pressing need of the day, climate change. We don't have the fundamental sort of basic equations of these phenomena. And we basically hit the limits of analytic models. And we see this in field after field after field, in economics, in medicine, in social sciences, and things like that. Something in the last 20 years, 25 years, a new kind of modeling approach started taking root, which is that you take a ton of data and you fit the curve. You basically say that I don't need simple causal equations, which are going to give me some insight into the phenomenon. I simply need lots of data, and I need an enormous amount of compute power. And this has been massively successful in the last 10 years. And somewhere along the line, it went from model building to machine learning to curve fitting to AI, and that has invoked a lot of enthusiasm, and the name has stuck. The first sort of wide, publicly acknowledged success of this approach was actually in something as mundane as spell correction in Google. Back in 2001, I wasn't there at Google then, but I believe a lot of people were trying to do spell correction with dictionaries and so on. It just wasn't working. And then you took a very simple model of spelling and misspelling, and then you used all the data on the web, and you built a model to predict what the actual spelling might be. It became an incredible hit. And people were like, what, you can just do this without a giant dictionary? After that, we've seen this kind of an approach have a huge impact in web search, advertising, news. And then, of course, in the last 10 years, we've seen a different class of models, which is deep neural networks, start taking over in vision and speech and things like that. One of the fascinating things is that most of the applications have been in the web ecosystem products. Things having to do with interacting with computers, and things having to do with web advertising, things having to do with web search, with online photos and things like that. The hope is that so much more can be done. There are all these pressing social problems, and we need to be able to apply these kind of modeling techniques much, much, much more widely. The real question is, what is keeping us from doing that? And I can go on, and years ago, I would have had to explain why there was a need for this. But today we see everywhere we look, and especially, in some portions of the talk, I'm going to focus on sort of the social demographics, and there's so much social inequality in every part of the world today, and on the climate issues. So what is holding us back when applying these approaches to 10x more problems? There's three pillars of data science machine learning. There's the algorithms, starting with the age-old regression to support vector machines to deep neural networks, LSTM, GANs, attention mechanism. Most of these things now, interestingly, are open source. You could go to GitHub and pick a reasonably good implementation of these things, and you should be able to apply it to your problem. Compute used to be a big issue, but now that we have these cloud vendors, GPUs and TPUs and whatever else that the acronyms are, you can pretty much rent the appropriate computing hardware in order to make this happen. The thing that is still proprietary, the thing that is still hard, very, very hard to come, is the data in order to train these machines, these models. And the reason why these advances that we see are coming from web companies, Google, Facebook, and so on, is because these companies have from their inception understood the value of data, and they have been collecting and organizing the data so that when it came time, when the opportunity presented itself, they were able to exploit this. So follow the data. Jim Gray used to say, follow the data. And the progress comes from large data sets. And the motivation or the inspiration for DataCommons comes from Jim Gray's Sloan Digital Sky Survey project. In the late 90s, Jim Gray collected, spoke to the major observatories in the world, and there's only a few, there's a fairly handful of them. And he he convinced them to give him a copy of their data. He organized it and created a single repository for it, and then provided online access to to students and researchers. It completely changed the nature of astronomy research. Before then, if somebody wanted to get a PhD in astronomy, they had to first write a grant proposal to go spend 6 months in an observatory. With this, you could stay at home and get an observatory, and there were PhDs being obtained by students from countries where there were no observatories. More recently, we've seen substantial impact on particular domains with corpora of well-organized corpora like ImageNet. So what is keeping us from actually creating similar repositories of data in a wide range of fields? Well, if you look at the data landscape, the problem is not a lack of data. If you look at societal data, in most countries, and I'm going to focus mostly on two countries in this talk, one is the US and the other is India, mostly because that is where most of our work has taken place. We have Census, we have RBI, we have UI, I can go on and on and on with the list of entities which spend an enormous amount of resources in gathering and republishing data about society. You have a similar situation happening in biomedicine. You have a similar situation happening in climate and energy. The problem is with using this data. If you had to go, figure out whether there's a correlation between X and Y, you have to forage for the data sets. You have to track down the assumptions. You have to clean and normalize and join, and then store the stuff. And then you try and build your model to see if your hypothesis is right. And there's a very high upfront cost. And given the cost, it makes experimenting very expensive. And there's a good analogy here with satellite imagery on the web. NASA had spent an enormous amount of resources over the decades in putting up satellite and collecting satellite data. When the web came around, there was a considerable amount of push on them to make their data public, which they did. They did go and put all their Landsat imagery up on the web. If you wanted to figure out what your house looked like from the sky, you could get the exact lat long of your house and then go to the appropriate website and then download the tiles. And once you download the tiles, there may be multiple tiles. You get this Java applet to stitch these tiles together, and then you get a different Java applet to view the tiles, and so on. Bottom line was that other than a handful of researchers, nobody really did this. A few years later, Google Earth and then Google Maps came along, and they did all this work and gave the data in an easily navigable form. Suddenly, it went from an esoteric thing for researchers to something that became part of everyday life, something that everybody just assumed you could have access to. We're in a similar situation today with data. If you look at data about is there in Census and Bureau of Economic Analysis and EPA, and there's 13 different US federal organizations whose sole job is to collect and disseminate data. Of course, they each do it in their own websites, in their own format, in their own schema. India is no better. India has a huge number of different, everything. The Ministry of Education has its own way of doing things. Health has its own way of doing things, and so on and so forth. Imagine instead of having to search for the data set and clean it and download it and normalize it and so on, you could just turn around and ask Google. You could just, if you wanted to do a more complicated analysis, it just comes with Python notebooks. The data should be part of the platform. The data is not something that you have to always load from the site. So this is our goal. And what we have, the DataCommons team has been doing over the last 3+ years is we've been building, so we've taken a large number of data sets. We first built a platform. Then we take a large number of these data sets. These are just some of these data sets. And you can find out the more complete list of data sets at datacommons.org, and built a giant knowledge graph. Now, first, why knowledge graph as a data model? Simply because when you have such heterogeneous data and you have, it's normal to think of it in terms of, or it's intuitive to think of it in terms of a set of entities, in this case, mostly places and businesses and so on, which are in relationship with each other. So, you could have a entity like, a city, and it has a school. So you have Chennai, which has IIT Madras, which is a university, which has other properties, and then you have statistics about these places and universities and these different kinds of entities. And a knowledge graph, which is a directed label graph, is very suited for this kind of data and is very easily extensible and so on. The schema becomes incredibly important. We've built our schema on top of schema.org. And this knowledge graph is just way too big for people to download onto their laptop or even the local data cluster and play with. They can do that if you want, and so we provide APIs so that applications of different sorts can be built easily. Now, it's really important to distinguish between this knowledge graph or a knowledge base versus a collection of data sets. There are collections of data sets like Harvard Dataverse, data.gov, and even Google has Google Dataset Search, which can search across data sets, which solve the problem of finding a data set. You still have to do the other things. You have to understand the context, you have to understand their schema, you have to clean it, join it, etc. DataCommons, on the other hand, is a single knowledge graph, which is being built where all of this stuff has already been done. So we built two things. One is an open source infrastructure for creating, storing, and serving these knowledge graphs. And the second is, and this includes it's nothing custom over here. We've built layers so that it's very easy to run a data commons on different clouds, even in a cluster of a few machines. The only requirement is that you need to be able to have a relational database somewhere there. And the ingestion pipelines are on GitHub. There are APIs in Python, REST, R. And then we've built 2+ large knowledge graphs on this infrastructure. One is what we call a societal knowledge graph, which is about demographics and education and so on. And the other one is a public health, biomedicine and public health knowledge graph. And we're just starting work on sort of an energy climate sustainability knowledge graph. So the societal knowledge graph has data, there's a lot of data from Census, US Census, Indian Census, a bunch of other places about demographics, including OECD, World Bank, and so on. There's a lot of data about education, health. There's a ton of data about economics, poverty, unemployment, employment, and some about, it's about 2 billion time series, and it's growing really rapidly. There's about 500,000 places, everything from, every county and census tract in the US to, county level places across the world to in India, we have every village and district, and not every village, but many villages and district level things, and so on and so forth. So an important question to ask whenever we go about building these massive structures is of what use is it? So I'm going to talk about the applications of the societal knowledge graph, and that gives us an indication of how we're thinking of proceeding across these different things, these different knowledge graphs or data commons. There's three categories of uses for the societal knowledge graph. One is for consumers, where I had mentioned, wouldn't it be great if somebody could simply turn around to Google and ask a question, or turn around to, this data is available to any search engine for a wide range of data that is available. For journalists who are willing to do more work and trying to go exploring, if there can be dashboards of simple exportable charts. For students and researchers, especially for students in data science courses, it would be a fantastic resource. So let me talk about the thing for consumers. The goal is, access to DataCommons via simple natural language queries, and we're starting with this on Google search, and then we will expand to other places. Right now, what we have already launched, and you can go to many of the things that I will show you today, you can access it on google.com and across a variety of languages. I think English, Spanish, French, German, and including Hindi, and so on. We're hopefully working on Tamil next, but it's going to take some time. Starting with simple time series questions, and then moving to more comparative data questions, and so on. So here's a very simple example. Hispanic population of California. So there's a question about demographics, and you want to be able to ask questions like this rather than having to hunt through different sources, not sure which one is from which census. Just get the data like this. Another one is, it's not just US, it's Europe too, male population of Berlin. And of course, it's not just simple population queries. This is a question about population growth. And you can see Berlin and Munich and all are pretty close to zero right now. And of course, we need Tamil Nadu. And it's female population, the population of women in Tamil Nadu. And it's not just at the state level, it's at the district level, and number of women in Chennai district. It's not just simple people queries, it's also things like households and jobs and so on. Moving on, we get questions in economics. It turns out that for a variety of obvious reasons, economics is really a topic which is super interesting, and there's lots of queries about this. White male population living in poverty in Atlanta. And there's many different interesting questions that come up over here, even in the context of like when somebody asks a question like that, what else do we show them, right? In this case, there's algorithms which pick out comparable cities. And it's interesting to note that, Atlanta versus Houston versus Chicago. India, how many poor people, how many people are poor in Tamil Nadu, meaning below the Indian government poverty line. And this one was actually quite fascinating to me because we've made an enormous amount of progress in Tamil Nadu, where the number of people below the poverty line has gone down by more than 50% over the last 10 plus years. This, of course, the Indian census data, it kind of ends in 2012 over there, and we're hoping that as the next round comes out, we'll get updated. The health-related queries, this is in the US county level about cancer-related deaths in Fulton County, which is in the state of Georgia. Fertility rate in India, again, another fascinating thing where the fertility rate is going down rather dramatically and has gone down from close to 6 in 1960 all the way to 2.2. It seems to be flattening down a little bit. It's still above that of the US and UK, but it's interesting, this trend. And it's also good to know that life expectancy is going up. It's still below the UK and US, but it's growing at a much faster clip than places over there. And energy is a big focus, and we have a ton of energy data that is already in, and we're getting more CO2 emissions. This is going up. This is not an area where we would like it to go up. It's fascinating to say things like, if you look at Bangladesh over there, what happened in 1970, and of course we all know what happened in 1970, around the 72 timeframe. But it's interesting to see history be reflected in these kind of statistics. In this, and it's a different lens to look at what happened. Per capita energy consumption is going up, and when energy consumption is often correlated with the prosperity levels, and it's interesting that the energy consumption has gone up by roughly 2.5 times, but the CO2 output is going up, seems to be growing more steeply, and these are all just interesting things to look at. And of course, any sequence of charts having to do with the environment has to cover earthquakes in California. It doesn't look good, but that's the way it is. So future consumer plans. Right now, the natural language interfaces are only on google.com. We are working with a team in Google Brain and some academics outside, where it should be possible to go to an open source natural language interface, where most of these corpora, the benchmarks, etc., that are there in the academic world are again static things where you run and see how well you're doing. It would be great if there would be, you can put up your interface and DataCommons backend will actually answer these queries. And much more challenging thing in the long term is you want to do much more than just simple point questions for which there were simple answers. Like, what's the population of Tamil Nadu? That's a straightforward answer. There may be multiple sources, but there's a single answer. But if a question like, what is the richest city in India, is really like, what do you mean by richest city? Is it the city where they're the richest people? Is it the city where the least number of poor people? Is it the city where the highest number of people in the highest income bracket? City with the highest median income? And when you have that, you have to actually come up with a different interface, a different way of answering and engaging in a dialogue with the user, just like you as a human being would engage in the dialogue if somebody were to come to you. And then there's open-ended questions. Tell me about literacy in Tamil Nadu. And you want to talk about not just the literacy levels, but how they're changing, the number of schools, and maybe even about the programs, and so on and so forth. As I mentioned, we're looking for research collaborations in these topics. If you're interested, drop us a line. Another set of queries, another set of applications has to do with data exploration tools. So data can add a lot of value to news articles, and we saw this especially during the pandemic, but the cost of having a data desk is so high that only a few media outlets seem to have one. This is our attempt to democratize that, and I'll show you a bunch of sort of charts and so on, where which are built using the same APIs that are available to everybody. And the whole idea is that you build a chart and you export the SVG or the data, and you can embed it anywhere. And the first of these things that we have is called place pages, and I'll actually show it to you live. And this is a query that I'm doing on Google. You can see the result over there. And what's interesting is that if you want to know more about Santa Clara County, you can go here, and this is on datacommons.org, and you get a ton of different data. Everything about how it ranks in the US, to its economics, to unemployment, its comparison with other counties that are around it, its poverty levels, its health. Of particular interest to me is this whole thing around equity, which is like, how does it compare? How does the median household income vary by race? And you can see clearly some races are doing better than others. How does it vary by gender? And it's kind of sad to see that even in this day and age, even in a place like Santa Clara, which is Silicon Valley, basically, male income is much higher than female income, and should not be the case. But and both are improving, but the gap is not reducing at all. Poverty levels by different race, poverty levels by gender, and you can see that women are more poor than men. And the whole point is you get this exposure, and then you can export this data, and then you can go. And it's of course not just the places in the US, it's places across the world. And let me see if I can look at Tamil Nadu. And you get, the data is not quite as rich, but it is getting there. We have everything from demographics and population density, and more and more and more data is going to be coming in. Another tool that we have is something called a timeline tool. This is a tool where this is a very simple tool that we can if you're interested. The interesting thing about this tool is you can pick one or a set of places and you can explore different variables. And if you look at this incredibly rich set of variables, if you're looking just at demographics, you have everything from all of these variables are available, and you can drill down on gender and female and so on and so forth. The thing that we look at now is we're all students, we're interested in university towns. How do different university towns vary by age? And these are some of the popular, big university towns in the US: Berkeley, Gainesville, Urbana-Champaign, Cambridge, Ann Arbor, College Station. And you can see all of these different things. And the whole idea is that this level of, and if you want to, you can just download the data or export the chart in another way, and then embed it wherever you want, and you're off. Another really interesting thing is a scatter plot explorer. So this is we've been talking, a lot of press has been on how COVID has affected certain demographics more than others. And it would be fantastic to be able to get that data trivially. This is an explorer where it's not about COVID, it's about in India, you look at a different state level, and this is the literacy, or the percentage of population which is illiterate compared to the percentage of population which is below the poverty level. And it's fascinating to see there are some states, AP has a very high illiteracy level, but according to the Indian data at least, but the poverty level is not that high. In contrast, you have some other places like Jharkhand where the illiteracy level, level is lower, but the percentage of people who are below the poverty level is incredibly high. And then we have Tamil Nadu somewhere right bang in the middle. Now the question is, like, if you want to say instead of illiteracy level, I just want to look at the female illiteracy level, right? Here, it should be that easy. Or instead of that, I wanted to look at, instead of people, instead of illiteracy level, I wanted to look at something different, like, are there rural people, rural population, and I want to compare that with the poverty level. That's that. Okay, it should be that easy. I'm not going to go into the meaning of the data and so on, but it should be that easy, and you should make it that easy to build. There are other tools over here that I won't get into. This is our population. There's a fantastic map tool, for example. This is California, and you can look at California county by median age, and you realize how some counties are much older than others. Or you can look at median income, and you realize that some counties are much richer. Or I know that a lot of students come here. And so if you want to look at something like the distribution by where are the Asians, you realize that the Asians are all mostly in a small number of counties, Alameda County, Santa Clara County, and so on and so forth. It should be this easy to explore, take the data, do whatever you want. So the future plans for these kinds of tools is these tools were built by us using our public APIs. Anybody should be able to, and we are not visualization people, anybody should be able to build an interesting suite of visualization tools. So we're making our APIs publicly available to everybody. and the hope that this, you shouldn't have to come here. The tool should be, visualization tool should be in your publishing platform. So we're trying to talk to everybody from WordPress to everybody so that they can embed these two APIs in their platforms. And at least at this point, with these APIs are free, we have a couple of companies which are starting to embed these APIs into their tools, so that when you say think of visualization API, you don't just think of APIs where you bring your own data. It comes with a ton of data that you can then, it's not just visualization, it's for correlation and this and that and so on and so forth. The third category of applications is for data science students. There's a ton of data science courses that are taking place. And I'm just going to very briefly talk about this in the interest of time. We already have in the online BSc course that IIT is offering, there's one of the faculties planning on using this data. And the idea is that this is, for example, an analysis of obesity that is done in a course at Berkeley, obesity as a function of blood pressure, unemployment, and poverty levels. If the students had to go find the data, gather the data, etc., this would be a multi-week exercise. But if the data comes with the platform, it becomes a much shorter exercise. And so this is blood pressure versus obesity, this is unemployment versus obesity, this is poverty versus obesity. And I bet that if you did the analysis for rural India, it would have a different kind of a shape, and urban India would have a shape similar to this. Okay. That's our societal KG. Let me just briefly go into sort of our infrastructure. And I'm going to leave some time for questions, so I'm not going to go that deeply into that. It's a very shallow dive. It's schemas, it's built on top of schema.org. We had to extend schema.org in many interesting ways to include function terms, temporal representation, provenance. One of the big issues that comes up again and again and again is provenance, because even for something non-controversial like the population of Tokyo, it turns out there are different sources. The UN believes one particular boundary line for Tokyo, Japan believes another boundary line, and then as you go beyond that into things like the number of COVID cases, of course, it becomes very controversial, and it's not our role to say this is the right data. It's simply our role to say XYZ reports that this is the data, which is very important that we keep the chain of attribution and provenance. APIs are fascinating. How do you build APIs for all the data in the world in a usable fashion? So we have 3 layers of APIs. One is a simple graph navigation API. Another one is a data log API that is used for really complicated analysis. And then we have a set of sort of domain-specific APIs that are used for things like the visualization tools and so on. And these domain-specific APIs know about things like, oh, this is a time series, this is a genomic sequence, and things like that. Storage is a big one. I won't go too deep into it. It's just that we need to be able to scale to 10 trillion tuples. Relational database technology is far more mature than graph database technology. Simple encodings into triple tables doesn't work. We've had to do a much more interesting thing where we store it in very relational friendly tables and then take graph queries like Sparkle and translate it. This result is that our KG scales our data with as much as BigQuery, which is one of Google's implementations of a relational database, and similar things. Scaling can be found in other clouds. I'm not actually going to go into the translator from Sparkle to SQL. If you're interested, just drop me a line. This is our overall architecture. We have a set of tables which look like very normalish tables from a relational perspective. We take the query. We have a language for mapping the graph, the relational schema into a graph schema. And the graph is provided, we call this graph as a view. So the graph is not actually stored as a graph, it's a view. And then, of course, in order to make it practically run at search level latencies, there's caches and a whole bunch of other things that are built on top. There's a couple of other things I want to talk about, and then I'll wrap up and take some questions. So another big DataCommons that we've been building, and in fact, in terms of its size, it's even bigger than the societal knowledge graph, is one around bio and biomedicine. And it also includes a bunch of public health data. If you look at biomedicines, there's several sort of what I call sub-vertical collections of data. There's the sequence people, there's the molecules people, there's the proteins people, and so on. It's also interesting because there's a lot of private data. We can't just open it up. And there's a lot of licensed data. And it started off, it has data for today from about 27 different sources. It's pushing 1 trillion triples. And the most significant metric for me is that we've already had 2 PhD thesis defenses feature DataCommons work prominently in them. Here is a smattering of the databases that are there in the biomedical database. Most of the access to it is through Sparkle because it's these complicated analysis that are done. And here is just an example of the kind of analysis that is enabled by it. So drug repurposing is a big, huge area of interest where a particular drug has already passed a variety of drug approval phases for a particular disease. So it's known to be safe and not have adverse effects and so on and so forth. If we can figure out, and given that there's only a limited number of distinct pathways in the human body, it would be great if we could retarget an existing a drug that has been approved for one purpose to a different purpose. Now, doing this requires sort of putting together data from a variety of different databases having to do with big molecules and sequences and diseases and huge number of things. And it's usually a giant exercise. The thing is that once you have the data, this was actually done. This is a collab notebook that you can find on our site, which goes through an exercise for drug discovery for Crohn's. And it actually turns out that this thing actually finds something. For better or worse, this of course, the pharmaceutical companies already knew about this particular drug. But the thing is that it can be done in a sort of a third of an internship project level project, as opposed to involving huge number of resources. So an interesting point about that comes up in medical data is there's a lot of non-open data that is licensed, or there's also a lot of data with very sensitive privacy issues. And an interesting part of the architecture over here is we're not trying to create a single data commons for the entire planet. There'll be many data commons, and you can layer one data commons on top of another. And it's the best way to think about it is how we have our intranets in our different companies or different institutions, and there's a portion of that is only work in that institutions. But they've not created a separate intranet or a separate web. This web is layered on top of the public web. There can be links from this internal web to the external web. And similarly over here, you can have a private data commons, which is layerable on top of the bigger public data commons. And we're working in a few different entities to create sample instances of the stuff. And in fact, I'm even hoping that if things go well, we will have one at the Bosch Center. A big focus of our recent effort is on energy climate data commons. Climate crisis, of course, touches on a very wide swath of topics. Everything from the actual temperature measurements to the vegetation covers, to fires, to floods, to housing, to agriculture, and the list goes on and on and on and on and on. Unfortunately, in way too many situations, decision making about the climate is not as data driven as it needs to be. And our hope, and I hope we're not being too naive, is that if you make the data much more easily accessible, it will lead to more data-driven decision making. It will lead to much easier research. It will lead to just better decisions. So there are three categories of uses that we're looking at initially. One is consumers and citizen scientists should be able to ask questions about emission, pollution, energy in just natural language on google.com. And it's not just google.com, the other search engines also have access to this data. Researchers should be able to create metrics for climate-induced insecurities that are caused in the economic realm, in health, in housing, for every county, for every country, for every district. The EPA in the US has something called EJ Screen, and it should be possible to create something similar to that or much richer than that for along many different dimensions, so that you can have an idea of exactly what is the the magnitude of the threat to the Ganges plain if under different scenarios. So I've read reports which say that there is a non-zero chance that the Himalayan glaciers, which feed the Ganges, might just completely melt, which would lead to, possibly a decade or more of incredible flooding, followed by many decades of some of the biggest droughts that mankind has ever seen. How do we actually model these things out? How do we understand these things? What's really happening? Here are some of the data sets that we're planning on including. Roughly a third of them are already in, and more are going in. Everything from IPCC data to NOAA, EPA, and there's also stuff from the Labor Department and OECD and NREL and so on and so forth, which is going into this. And we're actually, unlike the biomedical database, which is actually a distinct database, this is actually becoming part of the main DataCommons and APIs and everything we provided to everybody who wants it. One of the interesting things that we're trying to do over here with the Energy DataCommons is that it's not just a Google thing. We are trying to distribute this across multiple entities, across Google. There we have very good collaborators at the Magic Lab, Arun Majumdar from Stanford. We're talking Alyssa Goodman at Harvard is also starting to work with us, and maybe it would be fantastic to get IIT Madras involved. And we're also trying to make it so that it's not just on Google's cloud, it's on everybody's cloud over here. There's just too much work involved in building these beasts, and we shouldn't have to do it over and over and over again. So the long term, let me back out and conclude my presentation. The long-term vision is that we want to create and provide wide access to many different data commons. And these different data commons will differ based on the topic. Some of them will, they'll be focused on climate, they'll be focused on geo, public health, bio. They can be on multiple clouds. Some of them will be completely private, some of them will be semi-private, some of them will be completely public. Some of them will have different kinds of query tools and so on and so forth. But there are some common things, which are that the schema should be the same, and the query languages, even if the query tools are different, the query languages should be the same, so that you can actually retarget your tools. And if you build visualization layers, things which work on one data common should work on the other. It's not unlike a web browser where you don't go change web browsers or security protocols just because you're talking to a different website. And it's going to take quite a bit of work to bootstrap all of this stuff. And Google is, we are taking all the work that we've done, basically, all the code that is running DataCommons today, and offering it as a reference implementation. It's all available on GitHub, and all the data in DataCommons, and not just the data that is there today, but on a continuing basis to jumpstart the process of creating this stuff. So let me just end with one story, and it's a story that is being played out many, many, many times. It takes about 30 to 40 years from the time a new interesting technical innovation comes to the time where it finds its footing and it has its broadest impact. When TV came, the first applications were with people simply reading stories on TV. And it was 20, 30 years before they started realizing that they could actually have characters that are moving around. My favorite story along that line is the story of Aldus. Gutenberg came up with a printing press. He was a goldsmith. And before Gutenberg, there were a very small number of books in Europe, on the order of a few dozen. And they were almost all copies of the Bible, which had been handwritten. They were giant things, which you never, of course, closed. Each of them was chained to a desk. Aldus was a saddle maker who came over 30, 40 years after that. And he had this phenomenal idea, which is that you could put a book in a saddlebag, and which meant that you had to close a book, which meant that you needed page numbers, which meant that you needed a table of contents, and it changed the nature of what we thought as a book. And the first book that was actually bound this way was Martin Luther's translation of the Bible from Latin to German, which of course caused the Reformation and had a huge impact on the flow of history. Similarly, today, we've discovered empirical modeling, just barely discovered it, and we're using it in a point tool for a small number of things. But I do believe that if we can make data as ubiquitous as electricity is today. And it will have an impact which is on the order of what the printing press did. Thank you for attending, and let me see if I can attend at least a couple of of questions over here. Professor Ramanathan, is there one particular question? I see there's a lot of questions, and we have 7 minutes. I have no idea what our time constraints are. If there's some question that I should.
Sure. I mean, I can. So, I mean, the one question is about the privacy issues and how DataCommons gets around any such privacy issues that come up in making the.
So the data that this is a really good question. So there's two parts of the answer. One is the public data commons. We only take data that is already publicly available, and so we do not we do not try to keep private data at all. And so if the Indian census has published it, I'm assuming there are no universal guidelines, universal laws regarding privacy, right? And so we follow the local laws, and the best way to follow the local laws is to only take the data that has already been made public according to the local laws. Then there's the private data commons when we deal with hospital data, etc. And that data is basically, we don't try to anonymize or provide private access. It is only available to the owners of the data who they grant access to. Does that answer your question?
I guess so. So the other question is about both. I mean, there are two related questions. One is how is that you are able to merge data from so many different sources, and how do you handle the question of cleanliness or hygiene of the data?
Okay, so there are two distinct questions. One is the cleanliness and hygiene. There's two levels of the cleanliness hygiene question. One is you just get data in a variety of messy formats, and there is no magic silver bullet over there. We have a team of people who do the work in cleaning it up over a period of time. We've built a suite of tools that help us. The second part of it is there are some sources of data which are not as arguably as have used the same rigorous statistical procedures. And we are not people to complain that this is not, we don't want to be the judges. And so what we do is we keep the provenance and pass the provenance onto the user and allow the user to query by provenance. And the merging is a very big issue. The merging is we've developed a suite of techniques to actually, there is certain kinds of schema alignment which can be done only manually because it requires understanding the data. So in the US, the Census has two, and the Bureau of Economic Analysis have two different definitions of what a worker is. And unless somebody goes and understands that, it's really difficult you can't just smash them together. So we keep the entire trail of cleaning up, and also at some point somebody has to go look at it and do it. Now for the actual entity references and so on, we have built a set of tools internally and are expanding it and making it externally available, so that reference to Palo Alto, California in one place versus a FIPS ID in another place, and a place ID in a third place, and a Wikidata ID in another place can all be properly reconciled. And entity recon is a very big part of what we do.
So if any of the panelists have questions, they can unmute themselves and ask the questions. They can't type in the question and answer panel. Anyone?
Hello?
Yeah, go on.
Hello.
Yeah.
Hi, sir. So it's very interesting. I was wondering about the data aggregation. How much of this is actually sort of automated, and how expensive is it to add new data into this one graph?
So there's the schema alignment is only partially automated. The actual aggregation is all, of course, anything that is on the order of magnitude of the number of rows is automated. Things that are on the order of magnitude of the number of columns are typically not fully aggregatable, but they're partially aggregatable, for example. To just give you an idea, if you were to think of the US Census as one big table, the community survey table, which is the thing about people, it's about 25,000 columns. We don't, we do work on the order of, and many of them are combinations, and so there is partial algorithmic work. Number of rows is completely automated because we can't really, there's literally for every census tract, and there's tens of thousands of those things. Same thing in India, same thing in this. How difficult is it? We are simplifying, simplifying it, and there's people actually on the call who can, who will be able to give you a much better this thing because they're doing the work. The hope is to have, before the end of the year, a suite of tools where somebody with about an hour or two's training can start adding data to DataCommons, without much difficulty. Somebody who doesn't, who knows a little bit of Python or Java or something like that. That's the goal. And then by next year, we would like it to be the case that without even that level of programming knowledge, you should be able to do it. But there's a certain bare minimum below which we can't do. We can't go because somebody has to go understand the data.
Thank you.
Geeta, you had a question?
Yeah. So thanks for that wonderful preview to what is to come. So I was wondering, what about sensitive data? Is there any checks and balances that you include in the framework itself to classify data as sensitive, privacy issues and all that?
Yeah, since this is a debate that we go through at all times. It's just like what, and the question often boils down to who is it, what is sensitive and who is it sensitive to? There's sensitive data as distinguished from privacy, and I'm assuming I answered the privacy question earlier. Sensitive data, there's often data which is probably just, you don't know, for whatever reason, somebody doesn't want to put it out there. We have tended to be sort of Google, this is a Google project, and so we have tried, there's enough data, useful data out there before spreading into the sensitive ones. We've not gone there, but we do recognize that there may be partners and others who don't have those kinds of restrictions. And in those cases, we try and work with those people so that they can put up their own DataCommons. We still don't have an instance up like that, but that's the hope. There's also, similarly, there's an issue of who is publishing the data. There is some sensitivity from some governments about Google coming in and publishing their data. And so it would be fantastic. So if we had a datacommons.iitm.in, so where IITM becomes a single portal for all of Indian data that people can come and do things.
Yes, we would also love that, and we are hopefully working towards that as well.
Yeah.
So the Kriti has a question. So I don't know if you noticed, Kriti Ramanathan is also joined the thing. Do you have an active database interface, for example, traffic data that can help people plan their drive home?
You mean live data with very low latency for driving?
Yeah.
Oh, no, the latest, no, that you have to go to maps. The one which gets the data that gets updated most frequently is on the order of every few hours for the COVID data. Things like maps, etc. We've gone for data with a longer shelf life. There's nothing in our infrastructure which actually forbids us from doing data with our. I think right now and with our current architecture, the update time is still on the order of an hour to show up in search, an hour or two for unemployment data and COVID and a bunch of other things like that. We just haven't focused on that.
So I'll close the questions and thank Guha for really spending so much time with us. We also have a interaction session with the students. There is a link in the chat. So the people who signed up for the interaction session, if you can click on the link then and join the new Zoom meeting, which will be a smaller meeting for the people who signed up for interacting with Dr. Guha. So,
okay, great.
Thank you. Thank you once again, and see you in
Thank you again for having me, and we'll look forward to interesting collaborations.
Likewise. Thank you.
Thank you. Bye-bye.
Thank you so much.